Excuse the terrible trick of actually pointing a camera at a computer monitor. I'm not in the mood to muck around editing video files right now. This is a Bob the Science Guy video, but it's showing a Globebusters video.
And I was facing 186 degree azimuth, 35 degrees off the horizon. And we get the same thing. Dead straight, curving up, curving down. This is the moon, following the stars perfectly. Like I said, I'm just getting started looking into these star trails, but this is not a view I would expect to see from Denver, Colorado, but what I'd expect to see if I was standing at the equator.
And I'm going to pause him there and explain actually that's exactly what you would expect to see above the equator. What you are seeing, those straight lines up there, are above the equator. That's the celestial equator. Those things are hundreds or even thousands of light years away above the equator. The lines below them on the screen are stars that are above parts of the Earth south of the equator. The lines above those straight lines in your image, footage, whatever you want to call it, are caused by stars that are above points north of the equator. They're a lot more than 1,000 feet up. That's not why I was making the video, though. No, I was making the video because I get to do something rare and precious and special.
Okay, so here's his image. Now, we've got a couple of things here.
Zoom
First
out.
of all, he's identified this large, heavy streak as the moon. Now, the moon's diameter is about half a degree. Now, you can't really tell much from the streak.
The moon's diameter is half a degree, but obviously if he has his exposure settings right to show even the brightest of stars, the moon is horribly overexposed, so you can't say for sure what half a degree on that screen is. If you know the exact exposure time, you can work it out, because a 15 degree per hour drift. Thanks, Bob. But not from the width of that streak. Way too overexposed. The streak's at the wrong angle, by the way, with the dots next to them. Those are aircraft with a strobe light that goes off once per second.
But if you look at the width of that streak, the moon is a round object, so the width of the streak is also about half of a degree.
What's that got to do with it being round, Bob? What's that got to do with it being round?
Is the star trail. You see it's curving downward a little bit, and it's just underneath the beginning of the moon trail. Now, look at the length of that star trail. Go ahead and take a piece of paper and a pen, hold it up against the screen.
I'll take a screenshot and copy paste and make it 50% opacity, you know, that works too.
Compare the length of that to the length of the trail of the moon. This photograph is a 2.5 hour exposure.
There we go.
The moon moves approximately 1 moon width every hour.
37.5 degrees, in other words.
Compare the length of that moon trail to the star trail right underneath it.
So if this is a 2.5 hour exposure, you should have, at 15 degrees per hour, a 37.5 degree arc. But that's a 37.5 degree arc around the nearest celestial pole, or more accurately, around the Earth's axis of rotation. Right? So these star trails down here are 37.5 degree arcs around a point somewhere off the bottom of the screen. These ones up here are 37.5 degree arcs around a point somewhere off the top of the screen. These longer ones in the middle are 37.5 degree arcs around both at once, in effect. They're actually around the observer. How long an arc would Polaris make? How long an arc, in terms of pixels, not in terms of degrees, does, say, Vega make? And how long an arc does Mintaka, right over the equator, make? The reason the arc drawn by the moon here is longer than the arc drawn by this star here is that, well, It's really good that he didn't level the camera, isn't it? But if this one is 37.5 degrees, then we have that's 75 degrees, so across to here and all the way up to there would be about 120 degree field of view maybe. Right, so if that full field of view that way is 120 degrees, the height of it is maybe 90, probably a 4:3 aspect ratio. Right, so there's your celestial equator, and down here is something like 60 degrees south, 30 degrees north up here. The moon is actually considerably closer to the celestial equator, or was when this footage was made, than this star. The reason you get a longer arc here is the same as the reason that this arc here is longer than this arc here. It's closer to the equator.
Is it the same? Or is it a little longer? Now, if it's a little longer, it's because the moon is moving in relationship to the background stars. It's in orbit. In 2.5 minutes of a video by a flat earther, he not only managed to prove that the Earth is a rotating sphere, he also proved that the moon was in orbit around the Earth. Not a bad day's work. Thanks, Bob.
The moon, well, frames of reference. Is the moon in orbit around the Earth, or are the moon and the Earth in orbit around their shared centre of gravity? It doesn't actually make any difference. Do they go around the sun, or do they and the sun go around their shared centre of gravity? Not a lot of difference. When you start taking into account Jupiter and Saturn, you get all kinds of wibbly stuff, but from our point of view, the moon is orbiting the Earth, yes. But, Bob, the moon orbits the Earth west to east. That's why the first part of the moon that becomes lit up after a new moon is on the leading edge, the west side, and then it lights up from west to east as it goes west to east around to opposite the sun, and then it darkens from west to east as it goes west to east around to between us and the sun again. So actually, if you measured it as an angle rather than as a number of pixels, the star trail for the moon should be shorter than the star trail for a star at the same latitude, or, as it's a star, at the same declination, not longer. So, sorry, Bob. Now a question. How many flat earthers spotted that mistake? Let me guess. None.